Welcome to Key Players in the AI Industry. We're launching this series to create a clear, practical map of today's AI stack, from the silicon all the way to the end-user applications.
And in this rapidly evolving landscape, there's a central question we have to start with. Who is actually building the core intelligence? We see AI everywhere, but it all originates from a handful of what we call frontier labs. These are the organizations with the immense capital, talent, and computational power to push the boundaries of what these models can do.
It's a landscape dominated by just a few names, each with a distinct philosophy, architecture, and strategy for winning the future. Today, we're taking a deep dive into the four most influential players shaping the core of AI development: OpenAI, Anthropic, Google DeepMind, and Meta. Understanding their latest models and approaches is fundamental to understanding everything else that's built on top.
Think of it as meeting the architects before touring the city. Their design choices, their foundational beliefs about AI, are reflected in every subsequent layer of the industry. We'll start with the company that arguably brought large language models into the mainstream consciousness.
OpenAI. With GPT-5, they've introduced a fascinating new architecture focused on what they call unified reasoning. The model now automatically switches between a fast mode for simple quick response tasks and a thinking mode for more complex queries that require deeper analysis.
This is a crucial development for user experience and efficiency. It's like having two gears in a transmission. You don't need the full power of the engine to cruise on a flat road, which saves fuel. The fast mode handles the majority of everyday requests, summarizing an email, answering a quick factual question with incredible speed and lower computational cost. But when you ask it to, say, develop a multi-year business strategy based on 100 pages of market analysis, it shifts into that thinking gear, engaging more of its reasoning pathways. This dual-mode approach makes the model feel both instantaneous and deeply capable, depending on the need.
And this capability is being deployed across their entire product suite. Consumers interact with it through ChatGPT and its Pro plans, while developers are getting access to the more powerful GPT-5 Pro via the API. This is where we're seeing the most advanced applications being built. They've also finally released their video generation model, Sora, through the API, which has been a game changer for creative industries.
The release of AgentKit and new development tools is also significant. OpenAI isn't just building the model, it's building the ecosystem for others to create autonomous agents on top of it. They're providing the scaffolding for developers to build applications that can perform complex, multi-step tasks without constant human intervention. It's a clear signal that they see the future not just in chat, but in action.
Now, let's turn to their primary competitor, a company born from a different philosophy: Anthropic. While OpenAI has often been characterized by a move fast and build things ethos, Anthropic was founded with a safety-first mandate.
Exactly. And that philosophy is baked directly into their technology through a process they call constitutional AI. Instead of just relying on human feedback to align the model's behavior, they provide the AI with a set of explicit principles, a constitution, to guide its responses. This aims to make the model's behavior more predictable, controllable, and less prone to generating harmful or biased output. For enterprise customers, this is a massive selling point.
It's about trust and liability. If you're a bank using an AI to interact with customers, you need to be certain it won't go off the rails. Their latest models, Claude Opus 4.1 and Claude Sonnet 4.5, are leaning heavily into this. They claim Sonnet 4.5 is now the best coding model in the world.
That's a bold claim, and it's a direct shot at models like OpenAI's Codex and Google's Gemini. Coding is a perfect testbed for AI because it requires pure logic, creativity, and a deep understanding of complex systems. An AI that can write, debug, and optimize code effectively is demonstrating a very high level of reasoning. It's not just about spitting out code snippets, it's about understanding the programmer's intent. The improved instruction following and computer use capabilities mean the model can act more like a junior developer, taking high-level commands and executing them within a digital environment.
This brings us to the third major player, a true giant in the research world that is now flexing its commercial and product muscles, Google DeepMind. For years, they were known for groundbreaking but somewhat siloed research. Now, with the Gemini family of models, we're seeing that research power fully integrated into Google's vast ecosystem.
Their latest flagship, Gemini 2.5 Pro, is a beast. It's topping the LMA Arena leaderboard, which is a big deal because that leaderboard is based on anonymous, head-to-head human preference tests. It's not just about benchmarks. It's about which model people actually find more helpful and intelligent. Its performance on coding, math, and science benchmarks is state-of-the-art.
A key differentiator for Gemini is its architecture. It was built from the ground up to be natively multimodal. Unlike some earlier models that bolted on image or audio capabilities, Gemini processes text, images, code, and even video as a unified data type. This leads to a much more sophisticated and nuanced understanding of complex inputs.
The scale of its context window is also almost difficult to comprehend. We're talking about 1 to 2 million tokens. To put that in perspective, the entire Harry Potter series is about 1 million words, which would translate to roughly 1.3 million tokens. You could feed Gemini 2.5 Pro the entire saga and then have a deeply nuanced conversation about the foreshadowing in the first book that pays off in the last. For businesses, this means you can feed it an entire code base, a complete set of financial records for a decade, or all of your company's internal documentation, and it can reason across that entire corpus of information in a single query.
And Google's distribution strategy is immense. It's available for developers through Google AI Studio and Vertex AI, but it's also being pushed to consumers through the Gemini app and a new AI mode that's now active in over 200 countries. They are leveraging their global reach to get this technology into the hands of billions of users, integrating it directly into Search, Android, and Workspace. The new Gemini 2.5 computer use model even allows it to interact directly with a web browser, automating tasks that were previously impossible.
So we have OpenAI pushing the product frontier, Anthropic focusing on enterprise-grade safety and reliability, and Google integrating its state-of-the-art research across a global ecosystem. This brings us to our fourth and final player, which is taking a radically different approach, Meta.
With its Llama family of models, Meta has become the undisputed champion of the open weight movement. They're not trying to create the most powerful closed-source API-driven model. Instead, they're releasing incredibly capable models with a license that allows for broad commercial use, fostering a massive global community of developers who can build on, fine-tune, and run these models themselves.
Their latest release, the Llama 4 family, is a huge leap forward for open source. They've adopted a mixture of experts, or MOE, architecture for models like Scout and Maverick. This is a very clever design. Instead of a single monolithic model where all parameters are engaged for every single query, an MOE model is composed of many smaller expert networks. When a query comes in, the model's routing network intelligently selects just a few of the most relevant experts to process the request.
So, for a question about biology, it might activate the scientific reasoning expert and the natural language expert, while the coding expert remains dormant.
Precisely. This makes inference incredibly efficient. The Llama 4 Scout model, for example, has 109 billion total parameters, but only 17 billion are active at any given time. You get the knowledge and nuance of a very large model, but with the speed and computational cost of a much smaller one. It's the best of both worlds, and a key reason why open-source models are becoming competitive with their closed-source counterparts.
And the scale they are operating at is staggering. Llama 4 Maverick has 400 billion total parameters. There's even a 2 trillion parameter model, Behemoth, in a limited preview. But it's the context length of Scout that caught my eye. 10 million tokens. That's an order of magnitude larger than even Google's massive context window.
A 10 million token context window changes the game entirely. You're no longer limited to single documents or books. You could feed it an entire career's worth of research papers, an entire season of a television show's scripts, or years of financial data. It enables a form of analysis that is longitudinal and incredibly deep. Furthermore, the Llama 4 models are the first major open-weight models to be natively multimodal, just like Gemini. Meta isn't just catching up, it's innovating and pushing the entire open-source ecosystem forward.
Of course, it's not pure open source. The Meta Community License Agreement does have some restrictions for very large companies, but for the vast majority of startups and researchers, it's effectively a green light to build. They are also integrating these models directly into their own products, like Facebook and WhatsApp, which gives them a massive feedback loop for improvement.
So when you step back, you see four very different strategies. OpenAI is the product-led innovator, creating the most desired and powerful API. Anthropic is the safety-first partner for the enterprise, building trust through alignment. Google is the integrated giant, leveraging its research and distribution might to embed AI everywhere. And Meta is the ecosystem builder, aiming to commoditize the core intelligence layer and win by fostering a massive, open community.
Each of these labs is producing awe-inspiring technology, but a model, no matter how intelligent, is just a file on a server. For it to have any real-world impact, it needs to be powered by immense computational infrastructure and distributed to enterprises and developers at a global scale. An engine is useless without a vehicle to put it in.
Exactly. And that is where the strategic backers and cloud platforms come in. The symbiotic and sometimes competitive relationships between these labs and their biggest partners are what truly shape the market. And that's precisely where we'll be heading in our next episode. We'll examine the critical partnerships, like Microsoft's deep investment in OpenAI and Amazon's major stake in Anthropic, and how the cloud wars between AWS, Azure, and Google Cloud are being fought on the battlefield of AI. We'll also look at the foundational hardware layer and the absolute dominance of NVIDIA.
Welcome back to Key Players in the AI Industry. Last episode, we mapped out the frontier labs, the OpenAIs and the Google DeepMinds of the world, and the incredible models they're building. But those models, as powerful as they are, don't exist in a vacuum. They need a home. They need a foundation.
Exactly. It's one thing to design a world-class race car, but it's another thing entirely to build the factory, the racetrack, and the global logistics network to support it. Today, we're pulling back the curtain on the engine room of the AI revolution. We're talking about the cloud platforms and the colossal partnerships that provide the raw power for this entire ecosystem.
We'll start by dissecting the two most significant partnerships that are shaping the landscape: the deep alliance between Microsoft and OpenAI, and the equally formidable tie-up between Amazon and Anthropic. We'll then look at how Google is positioning its own cloud platform, Vertex AI, as a more neutral ground.
And from there, we dive into the bedrock of it all, the hardware. We'll explore NVIDIA's staggering dominance in the AI chip market and look at the competitors starting to gain ground. Finally, we'll zoom out to understand the broader platform dynamics, how enterprises are navigating this complex web of multi-cloud strategies, model marketplaces, and ever-present compliance hurdles.
These partnerships are more than just financial transactions. They are deeply symbiotic relationships that dictate the pace and direction of AI development. The models we discussed previously are computationally ravenous. Training them requires a mind-boggling scale of resources, and these cloud giants are the only ones who can provide it.
Think of it this way. If the AI labs are the brilliant composers creating the symphony, the cloud providers are the ones building the concert hall, manufacturing every instrument, and, most importantly, paying the electricity bill for a million-piece orchestra. You can't have one without the other.
Let's start with the partnership that has arguably defined the last few years of the AI boom: Microsoft and OpenAI. We're talking about a multi-billion-dollar investment, starting with $1 billion in 2019 and followed by another $10 billion. This isn't just a simple investment, it's a deep strategic alignment.
It's a textbook example of a symbiotic relationship. OpenAI gets nearly bottomless access to Microsoft's Azure, the global supercomputing infrastructure it needs to train its increasingly massive models. In return, Microsoft gets a massive stake in the leading AI research lab and becomes the exclusive cloud provider for OpenAI's API services. It's like they're the sole global distributor for the most in-demand product on the planet.
And this partnership continues to evolve. There's the Stargate project, a hugely ambitious plan to build a network of state-of-the-art AI data centers across the United States. While Microsoft isn't directly funding Stargate, which is backed by OpenAI, SoftBank, and Oracle, it shows the scale of infrastructure being built around OpenAI's needs. Legally, Microsoft has secured rights to OpenAI's intellectual property and maintains a right of first refusal on new capacity under their updated agreements, giving them a powerful position.
So, for an enterprise customer, if you want to use OpenAI's most powerful models via an API, you're doing it through Microsoft Azure. Microsoft has woven OpenAI's technology into its entire product stack, from GitHub Copilot to Microsoft 365. It's a brilliant move that transformed Azure into the go-to platform for developers wanting to build on top of GPT models.
But they aren't the only ones playing this game. Amazon has made an equally aggressive move by forging a deep partnership with Anthropic, one of OpenAI's primary competitors. Amazon has completed a $4 billion investment with a commitment that brings the total up to $8 billion, making them the largest stakeholder.
And just like the Microsoft OpenAI deal, this is about much more than money. A key condition of the deal is that Anthropic will use Amazon Web Services, AWS, as its primary cloud provider. This is a massive win for AWS, locking in one of the most promising AI labs. It's a strategic countermove to keep pace with Microsoft Azure.
A fascinating component here is the hardware. The deal stipulates that Anthropic will use AWS's custom-designed AI chips, Trainium for training and Inference for inference. This gives AWS a crucial anchor tenant for its homegrown silicon, allowing them to battle test and scale their chips against NVIDIA's best. Anthropic, in turn, gets to co-develop these chips, essentially creating custom hardware optimized for their Claude models.
It's like a Formula One team not just getting an engine from a manufacturer, but moving into the factory to help design the next generation. This deep integration is a powerful advantage, and we see the results in the market. Anthropic's models like Claude Sonnet 4.5 are now available on Amazon Bedrock, AWS's managed service for foundation models. This model is posting industry-leading benchmarks, especially in complex coding and agentic tasks.
Which brings us to the third major player, Google. Google is in a unique position because it has its own frontier lab, Google DeepMind, and its own state-of-the-art models with the Gemini family. But with its cloud offering, Vertex AI, it's taking a different approach.
Yes, instead of an exclusive partnership, Google is building what you might call a supermarket for AI models. Their Vertex AI Model Garden is a platform that hosts not only their own first-party Gemini models, but also a huge variety of third-party and open-source models. You can find Meta's Llama 4, models from Anthropic, Mistral, and over 200 other curated options.
The strategy here is choice. Google Cloud is betting that enterprises don't want to be locked into a single model provider. Vertex AI offers a unified platform where developers can easily discover, test, customize, and deploy the best model for a specific job, regardless of who made it. The platform is engineered for one-click deployment and native customization, which is a powerful selling point.
It's the Switzerland of AI clouds. If Microsoft Azure is the exclusive OpenAI boutique and AWS is the high-end Anthropic department store, Google's Vertex AI is the sprawling, comprehensive mall that has something for everyone. This appeals to businesses that want to de-risk their AI strategy and not tie their entire future to a single lab's roadmap. It's a compelling pitch based on flexibility and openness.
And none of this would be possible without the underlying hardware. This entire ecosystem is built on a foundation of silicon, and one company stands above all others, NVIDIA. Their dominance is staggering, with their H100 and H200 GPUs being the workhorses of the industry, and the new Blackwell B100 and B200 series pushing the performance envelope even further.
NVIDIA played this perfectly. For years, they built not just the best chips for parallel processing, but crucially, the software ecosystem around them, called CUDA. They created the picks and shovels for the AI gold rush long before most people even knew there was gold. As a result, almost every major AI model has been trained on NVIDIA hardware.
The scale of their partnerships is just as massive. For example, they recently announced a strategic partnership to deploy 10 gigawatts of their systems for OpenAI, with NVIDIA intending to invest up to $100 billion in OpenAI as the systems are deployed. That's not just a customer relationship, it's a co-investment in building the future of AI infrastructure.
But a monopoly, or near monopoly, invites competition, and we're starting to see serious challengers emerge. AMD is gaining ground with its MI300 and MI350 series chips, which are proving to be viable alternatives. And the cloud providers themselves are getting into the game, like we mentioned with AWS's Trainium and Google's own Tensor Processing Units, or TPUs.
There are also newer, more specialized players entering the field. Companies like Grok and Cerebras are focusing on high-throughput inference, which is the process of running a model rather than training it. They're building radically different chip architectures designed for pure speed on specific tasks. Cerebras recently raised another $1.1 billion, and Grok has raised hundreds of millions, showing their significant investor belief in these alternative approaches.
This points to a critical reality of AI infrastructure. It's not just about the raw compute power of the chip. The system is only as strong as its weakest link. A super-fast GPU is useless if it's starved for data.
Exactly. The true bottlenecks are often found elsewhere. Memory bandwidth, the speed at which data can be moved onto the chip, is a massive constraint. Networking infrastructure is another. Training a large model involves thousands of chips talking to each other, and if that communication is slow, the entire cluster sits idle. And then there's the sheer physical constraints of power and cooling. These AI data centers consume astonishing amounts of electricity.
Your analogy of a race car engine with bicycle tires is perfect. You can have a 1,000-horsepower engine, but if you can't get fuel to it fast enough or the tires can't handle the power, you're not going anywhere. The performance of the entire AI cluster is a delicate balance of compute, memory, networking, and power.
So let's bring this all together from the perspective of an enterprise trying to adopt AI. They're faced with this complex landscape of cloud model alliances and hardware choices. This has given rise to the concept of a multi-cloud strategy.
It's the logical response to avoid vendor lock-in. A company might use AWS Bedrock to access Anthropic's Claude for a coding-intensive task, but then use Google's Vertex AI to fine-tune an open-source model like Llama for a customer service chatbot. They want the flexibility to use the best tool for the job, and these cloud providers are facilitating that with their model marketplaces.
These marketplaces, AWS Bedrock, Azure AI Service, and Google's Model Garden, have become the central hubs for enterprise AI. They provide unified APIs, billing, and security, making it easier for businesses to experiment and deploy a variety of models.
But there's a final, crucial layer of complexity: compliance. For many organizations, especially in government or finance, the choice of vendor isn't just about performance or cost, it's dictated by regulations. A provider's ability to meet standards like FedRAMP in the US or strict data residency laws in the European Union can be the single most important factor in the decision-making process.
So the key takeaway here is that the AI revolution is being fought on multiple fronts. It's not just a race to build the most intelligent model. It is a war of ecosystems, waged with billions of dollars in strategic investments, exclusive cloud partnerships, and a relentless drive to control the underlying hardware.
That's the perfect summary. The frontier labs are the visible pioneers, but their progress is completely dependent on the industrial giants building the infrastructure beneath them. The two are now inextricably linked. The partnerships between cloud providers and AI labs are the new axis of power in the technology industry.
We've covered the models and the massive cloud and hardware infrastructure that powers them. But what fuels this entire engine? What is the raw material that these models consume to become intelligent?
Data. And that is where we are going next time. We will dive into the world of data acquisition and labeling, exploring the critical process of reinforcement learning from human feedback, or RLHF. We'll also unpack the fierce debate around data rights, copyright, and provenance that is shaping the future of how these models are built. It's a conversation you won't want to miss.
Welcome to Key Players in the AI Industry. In our last discussion, we mapped the staggering scale of the physical world of AI, the colossal cloud partnerships, the billions poured into infrastructure by Microsoft, Amazon, and Google, and the silicon dominance of NVIDIA. We looked at the engines. But an engine, no matter how powerful, is just inert metal without fuel. Which brings us to the core question for today's episode. What is the fuel that powers these immense computational engines?
And it's a fuel that's becoming more valuable and more contested than oil. We're talking about data. Not just the raw, chaotic flood of information on the internet, but the refined, curated, and precisely labeled data that transforms a statistical model into something that can reason, create, and converse. This is the foundation upon which everything else is built. It's the difference between a library with all the books in the world thrown into a pile and one where every book is cataloged, cross-referenced, and even has expert commentary in the margins.
Exactly. So today, we're moving up the stack from the hardware to the data itself. We'll explore how this critical resource is acquired and labeled, looking at the key players in that space. We'll then dive into the sophisticated techniques used to align models with human values, like RLHF and the emerging RLAIF.
And critically, we'll examine what truly makes data a competitive moat in this industry. Is it sheer volume or something else entirely? Finally, we'll wade into the increasingly murky legal and ethical waters of data rights, provenance, and the multi-billion-dollar question of who actually owns the information our AIs are trained on.
Let's start at the beginning of the pipeline, data acquisition and labeling. We have these massive pre-trained models that have ingested a huge chunk of the public internet, but that raw data is messy. How do labs refine it into something usable for sophisticated training?
This is where a specialized and fiercely competitive sub-industry has emerged. For years, the dominant name has been Scale AI. They are, in essence, the masters of annotation. Think of them as operating a global, technologically augmented workforce that takes raw data, images, text, sensor data, and adds the critical layer of human understanding. They're the ones telling the model, this part of the image is a car, this sentence expresses a negative sentiment, or this is a valid snippet of Python code.
So they provide the ground truth that models learn from. But I've noticed another name gaining significant traction recently, Surge AI. How are they differentiating themselves?
Surge AI has competed very aggressively, and reports suggest they're seeing incredible revenue growth by focusing on the specific needs of large language model development. While Scale AI built its empire on a broader set of data pipes, particularly for computer vision in autonomous vehicles, Surge has gone deep into the nuances of language. They specialize in the kind of high-quality, fine-grained feedback that's essential for improving conversational AI, reducing bias, and aligning models to complex human instructions. They are less of a general-purpose factory and more of a specialized, elite workshop for language data.
And this is still fundamentally about humans in the loop, which sounds expensive and difficult to scale. Is there an alternative?
There is, and it's one of the most important trends in the space: synthetic data. If real-world data is like filming a nature documentary, you have to wait for the right conditions and capture what you can, synthetic data is like building a perfect film set. You can generate an almost infinite variety of scenarios, especially for edge cases that are rare in the real world. For training a self-driving car, you can create thousands of simulations of a deer jumping into the road at dusk in the rain without ever needing to find that specific, dangerous event in reality. This is rapidly maturing from a niche technique to a core component of training pipelines.
So we have human-labeled real data and machine-generated synthetic data. But once the model has this initial knowledge, how do you steer it? How do you teach it not just facts, but also behavior, tone, and safety?
This brings us to the alignment process, and the most established technique is reinforcement learning from human feedback, or RLHF. This has been the standard across all the major labs: OpenAI, Anthropic, Google. The process is conceptually quite simple. You give the model a prompt, and it generates several possible responses. Human reviewers then rank these responses from best to worst. This feedback is used to train a reward model, which essentially learns to predict what kind of answers humans will prefer. The core LLM is then fine-tuned against this reward model, nudging it to produce outputs that will score highly.
It's like a continuous process of showing a student different ways to solve a problem and telling them which one is the most elegant or correct.
Precisely. But as you can imagine, just like with initial data labeling, relying on humans is a bottleneck. It's slow and expensive to get feedback on millions of potential outputs. This has led to the development of RLAIF, reinforcement learning from AI feedback.
Using AI to train AI. That seems both powerful and potentially fraught with risk. How does that work in practice?
Anthropic has been the pioneer here with their constitutional AI approach. The idea is to first use humans to create a set of guiding principles, a constitution. This might include rules like choose the response that is most helpful, avoid making claims you can't substantiate, or politely decline harmful requests. Then you use a separate AI model to generate responses and critique them according to this constitution. One AI generates, another AI provides the feedback signal based on the principles. This allows you to scale the feedback process enormously, generating vast amounts of preference data without needing a human for every single interaction.
So you're essentially bootstrapping the alignment process. The human role shifts from being a constant grader to being the philosopher king who writes the laws. And does this actually work? What's the impact?
The impact is significant. Models trained with these high-quality feedback loops, whether from humans or AI, show demonstrably reduced rates of hallucination and are better at navigating nuance and avoiding harmful or biased outputs. It's the core technology responsible for turning incredibly powerful but unpredictable base models into the more reliable and safer assistants we interact with today.
This all points to a broader theme, that the ultimate competitive advantage, the moat in the AI industry, might not be the model architecture or even the amount of compute you have. It seems to be access to the best data signals.
Absolutely. Raw data itself is becoming commoditized. Large-scale web scraping is something many can do. The real moat is the flywheel of high-quality, proprietary data and the infrastructure to process it. This involves several layers. First, there's the curation of the initial training set. Instead of just dumping in the entire internet, labs are getting much more sophisticated about filtering for high-quality sources, like scientific papers, curated books, and well-vetted code repositories.
And this is where that ultra-high-quality human-labeled data for fine-tuning comes in.
Yes, that's the second and perhaps most critical layer. Having a small dataset of exceptionally high quality can have an outsized impact on performance. This is the domain-specific data that enterprises have, or the painstakingly created datasets that labs build for specific skills, like advanced mathematics or coding. A few thousand examples of gold standard data can be more valuable than millions of mediocre ones for teaching a specific high-value skill. Think of it as the difference between a general education and a specialized PhD program. The latter involves far less material, but it's at a much higher level of depth and quality.
Which leads us to the most contentious part of this entire discussion. Where does this data come from and who gets to control it? The legal and ethical frameworks seem to be miles behind the technology.
They are, and the friction is becoming impossible to ignore. For years, the approach was scrape first, ask questions later. But now, the content creators are asking those questions very loudly in court. We are seeing major legal challenges from artists, authors, and news organizations who argue their copyrighted work was used to build multi-trillion-dollar enterprises without compensation or consent.
And the publishers are fighting back technologically as well.
Correct. We're seeing an arms race. On one side, you have AI labs deploying sophisticated web crawlers. On the other, publishers are using enhanced bot blocking technologies and developing new standards, like really simple licensing, to programmatically declare whether their content can be used for AI training. It's a move from a porous web to one with more explicit walls and gates.
So the likely path forward is not through the courts or through technological blockades, but through negotiation.
It seems to be. The major tech companies, OpenAI, Google, Apple, are now actively negotiating and signing direct licensing agreements with publishers. They are paying for access to high-quality, timely content. This is a fundamental shift from taking data to buying it. It ensures a steady stream of high-quality information for them, and it creates a new revenue stream for content creators.
This also has massive implications for compliance. With regulations like GDPR in Europe and the CCPA in California, you can't just be cavalier with data, especially personal data.
Exactly. The regulatory pressure is immense. It's pushing the industry towards more controlled and ethical data practices. We're seeing the adoption of data clean rooms, which are secure environments where data can be analyzed and used for training without the raw data ever being exposed. This is crucial for handling sensitive enterprise or user data. The entire landscape is shifting from an opt-out model, where you assume you can use data unless someone tells you no, to an opt-in partnership model, where access is granted through explicit agreements.
So, to summarize, we've moved from the brute force era of big hardware to a far more nuanced and complex era defined by data. The key players are not just those with the most GPUs, but those with the cleanest, best labeled, and most ethically sourced data, and the most sophisticated alignment techniques. The foundation is everything.
That's the perfect takeaway. The model is only as good as the data it learns from, and the future of AI will be shaped by the battles being fought right now over data quality, data alignment, and data rights.
It's a fascinating evolution. And now that we have a clearer picture of the hardware that runs the models and the data that fuels them, it sets the stage perfectly for our next episode. We'll finally open up the black box and look at the model architectures themselves.
We'll explore the convergence towards multimodality, where models understand not just text, but images, audio, and video in a unified way. We'll also dissect the powerful new paradigm of AI agents that can take action and use tools.
And we'll tackle one of the biggest strategic debates in the entire industry, the philosophical and practical differences between open source and closed source models, and how that is shaping the global AI landscape, from Silicon Valley to China and the EU. That's next time on Key Players in the AI Industry. You are listening to Key Players in the AI Industry. In our last episode, we delved into the lifeblood of AI, data. We explored how it's sourced, refined, and used to instill models with their capabilities. But if data is the fuel, what about the engine itself?
Exactly. We've talked about the ingredients, and now it's time to understand the recipe and the kitchen. The most sophisticated data in the world is useless without an architecture capable of interpreting it and a stable ecosystem to operate within. This is where the theoretical potential we've been discussing meets the cold, hard reality of engineering and geopolitics.
And that raises a crucial question that defines the current era of AI development. As these models become almost incomprehensibly complex, what are the fundamental design choices and strategic power plays that are shaping who wins, who loses, and what the future of this technology will even look like? It's a landscape that is shifting under our feet.
To get a handle on it, we're going to map out 3 critical territories today. First, we'll look at the convergence toward multimodal architectures, models that are breaking free from the constraints of a single data type. Then, we'll dive into the central philosophical and strategic battle of our time, the open versus closed model ecosystem. And finally, we'll zoom out to survey the global landscape, because this is no longer a story confined to Silicon Valley.
These topics are the essential next layer of our inquiry. Understanding the architectural shift to multimodality is impossible without appreciating the data foundations we covered last time. And the debate between open and closed systems directly influences everything from data provenance to the very applications that get built. Let's begin with convergence. For years, we thought of AI in distinct silos, a model for text, another for images, a third for audio. That paradigm is collapsing.
It's collapsing at an astonishing rate. We are witnessing a powerful trend towards unified systems that can fluently process and generate content across text, images, audio, video, and even code. These aren't just separate models bolted together. They are increasingly single, cohesive architectures trained from the ground up to understand the relationships between these different modes of information.
This unification is the technical prerequisite for the next major leap in AI, the emergence of capable agents. An agent can't be truly effective if it's deaf or blind. To operate autonomously in digital and eventually physical environments, a model needs to perceive and reason about the world in the same rich, multimodal way we do. We're seeing this now with large language models that are being given the ability to use tool APIs, to access external software, to maintain a memory of their interactions, and to execute multi-step tasks without constant human intervention.
I think a powerful analogy is the evolution of a smartphone. The first mobile phones just made calls, then we added text, then a separate camera, then a separate GPS module. The iPhone's revolution was integrating all of this into a single, seamless interface where apps could draw on the camera, the GPS, and the keyboard simultaneously. Multimodal AI models are at that same inflection point. They are becoming the integrated operating system for intelligence.
And what does that look like in practice?
Imagine a project management agent. You could forward it an email chain, text, a schematic of a new product design, image, and a recorded voice memo from a stakeholder meeting. The agent could then synthesize all of that information, identify the key action items, update your project board using a tool like Jira via its API, and then draft a summary report that includes both text and relevant diagrams. It's a level of integration that moves beyond simple task automation into genuine cognitive offloading.
And this leads us to an even more profound concept, world models. If an agent is to act effectively, it needs more than just reactive intelligence. It needs a predictive understanding of its environment. It needs to grasp cause and effect. This is where we see cutting-edge research in training models within enhanced simulation environments, virtual spaces where an AI can learn the physics of a system, whether that's a software environment or a simplified model of the real world.
This is the jump from being a brilliant librarian who can find any piece of information to a seasoned engineer who intuitively understands how the machine works and what will happen if you pull a certain lever. It's about building a foundational, causal understanding, which is absolutely critical for reliability and safety. But this immense power raises that second critical question we wanted to address. Now that we're building these incredibly capable, world-aware architectures, who should own them? Who gets the keys?
And that sets the stage perfectly for the great debate, the schism between open and closed AI ecosystems. On one side, you have the closed API-based systems from frontier labs like OpenAI, Google DeepMind, and Anthropic. On the other, you have a burgeoning movement around open weight models, championed by players like Meta with Llama, Mistral from France, and TII's Falcon from the UAE.
It helps to think of this as a strategic choice with massive downstream consequences. The closed system approach is like dining at a 3-Michelin-star restaurant. You get an exquisite, state-of-the-art meal prepared by the world's best chefs. It's reliable, safe, and comes with impeccable service. In the tech world, we call that an enterprise-grade service level agreement, or SLA. However, you have no access to the kitchen, you can't see the recipe, and you certainly can't modify the dish to your personal taste. You are a consumer of a finished product.
Whereas the open weights approach is like that same Michelin star chef deciding to publish their cookbook and sell you the exact same professional-grade ingredients they use. You are given the model's parameters, its weights. This allows you to set up your own kitchen, which means hosting it on your own servers, either in the cloud or on-premise. You have complete control. You can examine the recipe, understand how it works, and, most importantly, you can fine-tune it. You can add a little more spice, substitute an ingredient, and adapt the dish for your specific dietary needs or preferences.
But that freedom comes with responsibility. You need your own kitchen, which translates to significant computing resources. And you need to know how to cook, which requires in-house technical expertise. There's no one to call if you burn the sauce. You have full control, but also full accountability for performance, security, and alignment.
And we must be precise with our language here. Open isn't a monolithic category. The licenses for these open-weight models exist on a spectrum. Some, like Meta's Llama models, come with community licenses that might have restrictions on use by very large cloud providers. Others are more permissive, closer to the traditional definition of open-source software. This licensing detail is a critical factor for any organization choosing a path.
So how does a company make this choice? It's a strategic balancing act. Many are adopting a hybrid approach. For applications involving highly sensitive customer data or requiring the absolute highest level of performance and reliability with legal guarantees, they might rely on a premium closed API from a provider like Anthropic or Google. The security and compliance wrappers are built in.
But for building a unique, differentiated product that requires deep customization, an open-weight model is often the better choice. If you're creating a specialized AI tutor for organic chemistry, for example, you'd want to take a powerful base model like Mistral's and fine-tune it extensively on a proprietary dataset of textbooks and research papers. That level of specialization is something you can only achieve with full control over the model. It's a trade-off between the convenience and power of a closed API and the control and customizability of an open model.
This is not just a technical decision, it's a global one. The philosophical rift between open and closed development is now mapping directly onto the geopolitical landscape, which brings us to our third major topic. This technological revolution is being shaped by distinct national and regional strategies.
Absolutely. Let's start in China, where AI development is advancing rapidly, heavily aligned with state policy and national champions. Companies like Baidu and ByteDance are producing incredibly sophisticated models. However, they continue to face significant headwinds from limitations on their access to the most advanced semiconductor chips. This constraint forces a different kind of innovation, one that prioritizes algorithmic and architectural efficiency to get the most performance out of the hardware they do have access to.
It's a fascinating example of how external pressures can shape a technological trajectory. Then you have the Middle East, particularly the UAE and Saudi Arabia, which are making colossal investments in sovereign AI capabilities. The Technology Innovation Institute, or TII, in the UAE is the entity behind the Falcon models, which have been some of the most powerful open-weight models available globally. This isn't just about economic diversification, it's a strategic imperative to build and control their own foundational models, ensuring they aren't dependent on technology providers from either the US or China. It's a declaration of technological sovereignty.
We see a different flavor of that same sovereign impulse in the European Union. Their approach is heavily influenced by their regulatory environment and a strong emphasis on user rights and privacy. Initiatives like the Euro HPC for supercomputing infrastructure and Gaia X for federated data services are designed to build a distinctly European AI ecosystem. The focus is on creating trustworthy, transparent, and region-specific models that comply with regulations like GDPR from the outset.
So when you pull the lens back, you see the world isn't converging on a single way of doing things. The global AI landscape is a patchwork. You have the market-driven, dual-pronged open and closed approach of the US, the state-aligned, efficiency-focused approach in China, the investment-heavy, sovereignty-driven push in the Middle East, and the values and regulation-led strategy in the EU. These varying approaches to openness, privacy, and state involvement are creating a diverse and competitive global technology stack.
It's a truly fascinating and complex picture. We've seen how model architecture is evolving from single-purpose tools into integrated, multimodal intelligences that can perceive and act. And we've explored how the creation of these powerful systems is happening within a fractured global ecosystem, defined by the foundational tension between open and closed philosophies and shaped by distinct national ambitions.
The key takeaway is that the how of AI development is just as important as the what. The architectural choices being made today to build unified models, to release them openly or keep them proprietary, and the geopolitical context in which those choices are made will have profound and lasting consequences for decades to come.
This exploration of multimodal convergence, where models learn to process not just text but also images, audio, and video in a unified way, serves as the perfect launchpad for our next episode. We've discussed the architectural blueprints for handling these different data types.
And next time, we're going to tour the factory floor. We will take a deep dive into the breakout companies and tools that are mastering these non-text modalities. We'll explore the world of synthetic voice from players like 11 Labs and Play.ht, unpack the magic of image generation from Midjourney, Ideogram, and Stability, and look at the rapidly evolving landscape of AI video with platforms like Luma, Pika, and Runway. We're moving from the abstract architecture to the tangible, often startling creative output. Join us for that.
Welcome to Key Players in the AI Industry. In our last episode, we mapped the architectural landscape, contrasting the open and closed ecosystems and the rise of multimodal models. But theory only takes us so far. Today, we're moving beyond the blueprints to see what these models are actually building.
Exactly. If last time was about understanding the engine, today is about test driving the vehicles. We're exploring the world beyond text, where AI is learning to speak, see, create, and even interact with the physical world. We'll start with the startlingly human world of voice and speech AI.
From there, we'll dive into the vibrant and sometimes surreal canvas of image generation, where text prompts blossom into photorealistic scenes.
Then we'll tackle the next great frontier, video synthesis. We'll look at the tools that are starting to generate moving pictures from mere descriptions and discuss the immense challenges and opportunities that come with that power.
And finally, we'll step into the third dimension, looking at how AI is beginning to generate 3D models and power-embodied agents, from robotics to complex digital simulations. These aren't just isolated technologies, they represent the sensory expansion of AI, giving it a voice and eyes on the world.
And understanding this expansion is critical. It's where the abstract power of large models translates into tangible tools that are reshaping entire industries, from entertainment and marketing to manufacturing and scientific research. Let's start with the one we're using right now, the human voice.
The progress here has been astronomical. Just a few years ago, text-to-speech, or TTS, was robotic and easily identifiable. Now, we're at a point of near-human quality synthesis. What's happening under the hood to enable this leap?
It's a convergence of incredibly powerful deep learning models trained on vast datasets of human speech. They're not just converting text to phonemes anymore. They're learning prosody, cadence, intonation, and even the subtle emotional cues that make a voice sound authentic. It's less like a machine reading words and more like a skilled actor performing a script. The model understands the context and delivers the line with the appropriate feeling.
And companies like 11 Labs have really capitalized on this, offering not just high-quality voices, but real-time voice cloning and generation. This seems to be one of the most immediate and accessible applications of generative AI.
It is, because voice is such a fundamental interface. Think about the use cases. In customer service, you can now have automated agents that are not just intelligent, but also warm, empathetic, and patient, completely transforming the user experience. This goes far beyond the press 1 for sales model.
I can see the impact for accessibility tools as well, giving a natural-sounding voice to those who cannot speak, or reading digital content aloud in a way that's engaging rather than draining.
Absolutely. And then there's the entire creator economy. Podcasters, audiobook narrators, and video producers can generate professional-grade voiceovers in any language, or even clone their own voice for consistency and scale. We're also seeing real-time translation applications that don't just translate the words, but preserve the speaker's original vocal identity, which is a massive leap for global communication.
Of course, with voice cloning comes significant ethical questions. But moving from the auditory to the visual, the explosion in image generation has been just as profound. We have a suite of powerful tools now: Midjourney, Stability AI's various models, Ideogram, and even Google's Gemini 2.5 Flash image. What are the key features that have pushed this from a novelty to a professional-grade tool?
3 things have been transformative. First is enhanced style control. You're no longer just rolling the dice on the aesthetic. You can command the model to replicate anything from 17th century Baroque painting to modern cinematic lighting with incredible fidelity. The second, and arguably the most important for practical use, is character consistency.
That's been the holy grail for a while, the ability to generate the same character in different poses, settings, and expressions.
Precisely. Early models would give you a different person every time, making them useless for any kind of sequential narrative, like a graphic novel or a marketing campaign. Now, you can create a character and reliably place them in a dozen different scenarios. This is a game changer for branding and storytelling. It's like the difference between hiring 100 random extras versus having a dedicated actor for a role.
And the third feature?
Natural language editing. The ability to say, make the car red, or add a mountain in the background, and have the model intelligently edit the existing image. This moves the process from pure generation to a collaborative dialogue, making it a much more intuitive and powerful creative partner.
The business applications are obvious. Marketing teams can prototype entire campaigns in an afternoon. Architects can visualize buildings. Product designers can generate endless variations of a concept. It's a massive accelerator for any visually driven industry.
It completely redefines the economics of content creation. The cost and time required to produce high-quality, bespoke imagery has plummeted, democratizing a capability that was once reserved for those with large budgets for photographers and graphic designers.
If generating a perfect, static image was the last challenge, generating a coherent, moving video is the next mountain to climb. We're seeing pioneers like Runway and Pika Labs, along with major players like Meta with Make a Video, and of course the technology that stunned everyone, OpenAI's Sora. This feels like a much harder problem.
It's exponentially harder. A static image needs to be spatially coherent. A video needs to be temporally coherent. Every frame has to logically follow the last one. Physics has to remain consistent. An object that is dropped must fall. A character walking must maintain their gait and appearance. Early video models struggled with this. You'd see people's faces melt or an extra limb suddenly appear.
The uncanny valley is much deeper when things are in motion.
Much deeper. Think of it this way. Generating an image is like composing a single photograph. You worry about lighting, composition, and subject. Generating a video is like shooting a movie. You are the director, the cinematographer, the set designer, and the physicist for the entire universe. And you have to ensure every single one of the thousands of frames makes perfect sense in relation to all the others. The computational complexity is staggering.
Yet, we are seeing incredible progress in overcoming these challenges, particularly with lip sync and maintaining object permanence over longer clips, though it's still not perfect. Where is this finding a foothold in the enterprise?
The most immediate applications are in short-form content. Think video advertising, social media content, and product demos. You can now generate a dynamic 30-second ad spot for a fraction of the cost of a traditional video shoot. It's also making waves in virtual production for film and television, allowing creators to quickly generate background plates or pre-visualized complex special effects sequences. And for corporate training, you can create bespoke, interactive video scenarios at scale.
With video, the potential for misuse is even greater than with voice or images. Deepfake videos could have serious societal consequences. How is the industry addressing this?
This is a critical point. The responsible players are actively working on mitigation. A key initiative is the adoption of content provenance standards, like C2PA, which stands for the Coalition for Content Provenance and Authenticity. This involves embedding a secure cryptographic signature into AI-generated content. This signature acts like a digital watermark, allowing anyone to verify the origin of the video and see if it was created or modified by an AI. It's not a foolproof solution, but it's a vital step towards creating a verifiable media ecosystem.
So, we've covered sound, sight, and motion. The final step is depth and interaction. 3D and embodied AI. This feels like the most futuristic domain, but it's already happening with tools like Luma AI and Google's Dream Fusion.
It is. These tools are starting to master NeRFs, or neural radiance fields, which is a sophisticated way to create a 3D scene from a collection of 2D images. You can take a few photos of an object with your phone, and the AI can construct a fully navigable 3D model. The quality is improving at a breakneck pace. This has enormous implications for gaming, virtual reality, e-commerce, and industrial design. Imagine being able to scan your living room and have an AI generate a 3D model that an interior designer can then redecorate in real time.
And this connects directly back to our previous discussion on world models. This isn't just about creating static 3D assets. It's about creating interactive environments where AI agents can learn and operate.
Exactly. This is where we see the convergence with robotics. An LLM can now provide high-level reasoning for a robot. For example, you could tell a robot, clean up the spilled coffee, and the model can translate that abstract command into a sequence of physical actions. Locate the spill, find a cloth, wipe the surface, and dispose of the cloth. To do this effectively, the robot needs to understand the 3D space it's in.
So these generative 3D models are providing the training grounds, the simulation environments for the next generation of robotics.
Precisely. You can create a digital twin of a factory floor or a city street and have an AI agent train for thousands of hours in that simulation before it ever encounters the real world. This makes training safer, faster, and vastly more scalable. The future here is about physics-based simulations powered by these generative models, allowing us to model incredibly complex systems, from climate patterns to molecular interactions with a level of fidelity we've never seen before.
It's an incredible trajectory. We've moved from AI as a text processor to a multimedia creator that can hear, see, and generate sight, sound, and motion. Now, it's developing a sense of space and physicality, allowing it to interact with and simulate our world. The speed of this evolution across all modalities is truly the defining story of the current AI landscape.
And it highlights that the value is no longer just in the foundational model itself, but in how these diverse, specialized capabilities are being applied. Each modality, voice, image, video, and 3D, is unlocking new products, services, and creative possibilities that were simply science fiction a few years ago.
But all of this incredible generation, all this sight and sound, comes at a cost. Creating these complex models and running them at scale requires an astronomical amount of computational power.
It's the bedrock on which this entire ecosystem is built. Without the specialized hardware and the sophisticated infrastructure to run it, none of this is possible. The economics of training versus inference, the competition in the chip market, these are the factors that will ultimately dictate the pace and direction of future innovation.
Which is the perfect entry point for our next episode. We'll be moving down the stack to explore the very foundation of this revolution, the infrastructure and economics of AI. We'll look at the multi-billion-dollar price tag for training a frontier model, the hardware arms race dominated by giants like NVIDIA but challenged by competitors like AMD and Google, and the clever software optimizations being used to manage these immense costs. Join us next time for AI Infrastructure and Economics. Welcome to Key Players in the AI Industry. In our last episode, we explored the explosion of generative AI beyond text into the realms of photorealistic images, compelling video, and lifelike synthetic voices. We saw what these models can do, but it begs a fundamental question. What is the true cost of this AI magic? What is the colossal engine running under the hood that makes it all possible?
It's a critical question because the answer isn't just about clever algorithms. It's about physics, economics, and a global supply chain of silicon. The story of AI today is as much a story about infrastructure as it is about intelligence. That's what we're diving into today, the physical and financial bedrock of the AI revolution. We'll start by dissecting the two fundamental economic forces at play, the cost of training these massive models versus the cost of running them for users.
From there, we'll map out the hardware battlefield. We'll look at the undisputed king, NVIDIA, the challengers like AMD and Google rising to meet them, and even some of the more exotic specialized chip makers. And we'll discover that the biggest challenges aren't always in the silicon itself, but in the physical bottlenecks of power, cooling, and connectivity.
And finally, we'll explore the clever bag of tricks that engineers are using to tame these costs. We'll talk about optimization techniques that are crucial for making AI not just powerful, but also practical and profitable. Understanding this infrastructure layer is non-negotiable for anyone building, buying, or investing in this space, as it fundamentally dictates the art of the possible.
Let's begin with that core economic divide, training versus inference. When we hear about a new frontier model costing billions of dollars to create, we're talking about the cost of training. This is a monumental upfront investment.
It's helpful to think of it like this. Training a frontier model is like designing and building a single, state-of-the-art Formula One car. The research and development, the exotic materials, the wind tunnel testing, the army of engineers, it all culminates in a multi-billion-dollar one-time effort to create the most powerful machine possible. This happens in highly specialized factories, or in our case, massive, purpose-built data centers packed with tens of thousands of GPUs, all working in concert on a single, Herculean task for months on end.
Exactly. And the computational requirements are staggering. We're talking about numbers that are hard to grasp. This is a capital expenditure of the highest order. But once that car is built, once that model is trained, the economic equation flips entirely. Now you have to actually race it. You have to run it. That's inference.
And inference is the cost of every single lap around the track. Every time a user asks a question, generates an image, or translates a sentence, that's one lap. While the cost of a single lap is minuscule compared to the cost of building the car, you're going to be running millions, even billions of laps. Over the lifetime of the model, the cumulative cost of fuel, tires, and race day logistics, the inference costs, will dwarf the initial manufacturing cost. This is an operational expenditure, and managing it is the key to a sustainable business.
This distinction also dictates the physical architecture. Training clusters are these centralized behemoths, optimized for one thing, a massive parallel processing job. Inference, however, has to be distributed. For low latency, you need the models running in data centers all over the world, close to your users. The architectural challenge shifts from an all-out sprint to a global concurrent marathon.
This marathon is run on very specific hardware, which brings us to the silicon arms race. And in that race, there is one company that has a commanding lead.
NVIDIA. Their H100 and H200 GPUs have become the default engine for the AI industry. And they're not standing still. Their next-generation Blackwell architecture, the B100 and B200 chips, promises another significant leap in performance. But their dominance isn't just about having the fastest chip. Their true moat is their software ecosystem, CUDA, which developers have been using for over a decade. It's the familiar, well-supported programming environment that everyone knows how to use.
It's created incredible lock-in, but the demand is so high and the price point so steep that it has created a massive opening for competitors. This isn't a one-horse race anymore. AMD is making a very serious play with its MI300 and forthcoming MI350 series accelerators. They're competing aggressively on both performance and price performance.
And you also have the cloud giants building their own custom silicon. This is a crucial strategic move for them. Google has been a long-time player with their tensor processing units, or TPUs, now in their 5th generation. Amazon Web Services has its Trainium chips for training and Inferentia chips for inference. By designing their own hardware, they can optimize it for their specific software and infrastructure and insulate themselves from NVIDIA's pricing power. It's a move to control their own destiny.
It's like the top racing teams deciding they need to build their own engines in-house to get a specific edge, rather than just buying them from a third-party supplier. Beyond these giants, you have fascinating startups tackling the problem from new angles. Grok, for instance, has developed what they call a language processing unit, a tensor processor designed for one thing: extreme low-latency inference. They're not trying to be the best at training, but the absolute fastest at running the model.
Then there's Cerebras, which takes a completely different approach with its wafer-scale engines. Instead of dicing a silicon wafer into hundreds of individual chips, they use the entire wafer as one massive chip. It's a radical design aimed at very specific, massive-scale scientific and AI workloads. These are the boutique engineering firms, not building for the mass market, but for very specific high-performance use cases.
But the silicon is only part of the story. The real-world performance is often dictated by the bottlenecks around the chip. Imagine you have the most powerful car engine ever built. If your fuel line is too narrow, you can't get enough gasoline to it. If the axles are weak, they'll snap under the torque. AI hardware faces the exact same problems.
A primary bottleneck is memory bandwidth. These AI models are enormous, and you have to constantly feed the processing cores with data from memory. The speed at which you can do that is critical. This is why you hear so much about high bandwidth memory, or HBM. Another is the interconnect, the high-speed networking that links thousands of these chips together to work as one. NVIDIA has NVLink, and the broader industry standard is InfiniBand. This is the central nervous system of an AI supercomputer. Without a fast enough interconnect, most of your expensive processors will just sit idle, waiting for data.
And then we get to the really unglamorous but utterly critical constraints: power and cooling. A single AI data center can consume as much electricity as a small city. We are talking about hundreds of megawatts. That power generates a tremendous amount of heat, and if you can't get that heat away from the chips efficiently, they'll throttle down or even fail.
This is driving a huge push towards greater efficiency and sustainability, not just for environmental reasons, but for economic ones. Power is one of the biggest operational costs. We're seeing a shift from traditional air cooling to much more efficient liquid cooling systems, where coolant is piped directly to the components. It's also why you see data centers being built in colder climates or strategically located next to massive renewable energy sources. You have to cool the beast, and you have to power it affordably.
So, with these enormous hardware costs and physical constraints, the pressure to be more efficient on the software side is immense. You've spent billions on your Formula One car. Now you need a brilliant race strategy to win. This is where serving optimizations come in, the collection of software techniques that allow us to run these models faster and cheaper.
One of the most impactful techniques is quantization. Most models are trained using 16-bit floating point numbers, which offer a high degree of precision. But for inference, it turns out you often don't need that much precision. Dynamic quantization involves running the model with smaller data types, like 8-bit or even 4-bit integers. This drastically reduces the model's memory footprint and can speed up computation because you're moving less data around.
The analogy is using a slightly less detailed map to navigate a city. For finding your way from point A to point B, you don't need a map that shows every single crack in the sidewalk. A simpler map is faster to read and lighter to carry, and it gets the job done just as well for most purposes. That's what quantization does for these models.
Another key optimization is KV caching. When you're having a conversation with a language model, with each new turn, the model has to reprocess the entire conversation history to understand the context. KV caching is a clever trick where the model stores the intermediate calculations from the earlier parts of the text, the key and value states in the transformer architecture. That way, it only needs to perform new computations on the newest piece of text.
It's like a chef preparing for a multi-course meal. For the first course, they chop the onions, carrots, and celery. For the next course that also uses those ingredients, they don't start from scratch. They use the vegetables they've already prepped. KV caching is that prep work. It avoids redoing calculations that have already been done, dramatically speeding up conversations and text generation.
We're also seeing a move away from fine-tuning the entire model for new tasks, which is incredibly expensive. Instead, the industry is embracing techniques like PEFT, or parameter-efficient fine-tuning, with LoRa being one of the most popular methods. You freeze the massive pre-trained model and then train a very small set of new parameters, tiny adapter layers that plug into the main model.
This is a game changer. It's like having a master mechanic with a comprehensive, universal set of tools. When a new car model comes out, you don't build a whole new garage and hire a new mechanic. You just give your existing expert a small, specialized new tool for that specific car. LoRa is that specialized tool. It allows you to teach a massive model a new skill at a tiny fraction of the computational cost.
And then there's the architectural level, with techniques like model distillation and retrieval augmented generation, or RAG. With distillation, you use a large, powerful teacher model, like a GPT-4, to train a much smaller, faster student model. The student learns to mimic the outputs and reasoning patterns of the teacher, packing a surprising amount of capability into a much more efficient package.
RAG fundamentally changes the role of the model itself. Instead of trying to force the model to memorize the entire world's knowledge in its parameters, which makes it bloated and expensive, you give it access to an external knowledge base, like a search index or a document database. When a query comes in, the system first retrieves relevant documents and then feeds that information to the model as context. The model's job shifts from knowing everything to reasoning on the information it's given. It's the difference between memorizing an entire encyclopedia versus just knowing how to look things up. It leads to smaller, cheaper models that provide more accurate and up-to-date answers.
So when you pull it all together, you see that the incredible AI applications we talked about in the last episode stand on top of this massive complex pyramid. The entire industry's trajectory is shaped by the economics of training versus inference, the intense competition in the hardware space, and this constant, relentless drive for software optimization.
The key takeaway really is that the story of AI has become a story of physical and economic realities. It's about managing heat, power, bandwidth, and billions of dollars in capital. The most profound innovation isn't always happening in the algorithmic ether, but in the gritty, tangible engineering that makes running these models in the real world feasible.
We've covered the models and the physical infrastructure they run on, but there's a crucial layer in between, the tools developers use to actually build reliable applications on top of this incredibly complex stack. How do you chain these models together to perform multi-step tasks? How do you monitor their performance and catch problems in production? And critically, how do you ensure they operate safely and responsibly?
That's the perfect bridge to where we're going next. We're moving up the stack from the silicon to the software development kit. In our next episode, we'll explore the world of AI development tooling. We'll look at the powerful agent frameworks like LangChain and Llama Index that act as the connective tissue for sophisticated AI workflows, the essential observability platforms that are our eyes and ears in production, and the governance frameworks that provide the guardrails to keep these powerful systems aligned with our goals. It's the next piece of the puzzle in building real-world AI.
You are listening to Key Players in the AI Industry. We've spent our last discussion deep in the engine room, talking about the raw power, the economics of training, and the specialized silicon from giants like NVIDIA and Google that makes this entire revolution possible. But having a powerful engine is one thing. Building a sophisticated, reliable vehicle around it is another entirely. How do we move from a raw, probabilistic model to a dependable, production-grade application that can perform complex tasks safely?
That's the central question for developers and enterprises today. We've established that the underlying infrastructure is a marvel of engineering, but also fantastically expensive and complex. Getting a model to generate a response is now the easy part. The real engineering challenge is orchestration. How do you make a model reason, use tools, and remember past interactions? How do you monitor its performance when it's constantly surprising you? And critically, how do you put guardrails on it to ensure it doesn't go off the rails?
Precisely. So today, we're moving up the stack from the hardware to the software layer that makes AI truly functional and trustworthy. We'll start by exploring the brains of modern AI applications, the agent frameworks like LangChain and Llama Index that enable models to execute complex multi-step workflows. Then we'll shift to the nervous system, the critical monitoring and observability platforms like Arise AI and Weights and Biases that watch for problems like drift and bias.
And finally, we'll discuss the conscience of these systems, the governance and guardrail frameworks that are essential for safe and compliant deployment. This is the toolkit that separates a fascinating demo from a billion-dollar enterprise product. It's about building systems that are not just powerful, but also predictable, manageable, and accountable.
Let's start with those agent frameworks. The term agent is everywhere now. What does it actually mean in this context, and what are tools like LangChain or Microsoft Semantic Kernel actually doing?
At their core, these frameworks are orchestrators. Think of a large language model as an incredibly talented, knowledgeable, but very literal-minded junior chef. It can chop, sauté, and plate flawlessly when given a single clear instruction, but it can't plan a whole banquet. An agent framework is the head chef. It takes a complex, high-level goal, say plan, source, and prepare a 3-course meal for a dinner party of 8 with a vegetarian option, and breaks it down into a sequence of concrete steps.
So it's a layer that adds reasoning and planning capabilities on top of the model's raw generative power. It transforms the model from a simple text-in, text-out function into something that can execute a process.
Exactly. The framework provides the scaffolding for this process. It does a few key things. First, there's planning. The framework helps the model decompose a large task into a chain of smaller, manageable prompts. Instead of one giant, complex prompt that's likely to fail, you have a series of focused queries. Second is tool use. This is absolutely critical. The head chef knows they can't do everything themselves. They need an oven, a blender, a thermometer. An agent framework gives the LLM access to tools, which are just external APIs.
This is what allows an AI assistant to check the current weather, search the web for recent information, or access a private company database, right? The model itself has static knowledge, but the framework allows it to fetch and incorporate live external data.
Correct. LangChain, for example, has a massive ecosystem of pre-built integrations for hundreds of APIs. The framework manages the entire process. It helps the LLM recognize when it needs a tool, formats the query to the API, takes the API's response, and feeds that new information back into the model to generate the final answer. The third and final piece is memory. The head chef needs to remember what's already in the oven and what still needs to be prepped. Agent frameworks provide memory modules that allow the AI to retain context over a long, multi-turn conversation, preventing it from forgetting what was discussed a few minutes ago.
So these frameworks are really about creating stateful, persistent applications, moving beyond the simple stateless request-response paradigm. You're not just prompting, you're engineering a workflow. This seems like a fundamental shift in how developers interact with these models.
It is. It abstracts away a lot of the complexity of prompt chaining and memory management, but it also introduces its own challenges. These chains of calls can become very complex, difficult to debug, and potentially slow. However, they are the foundational technology for building the sophisticated co-pilots and autonomous agents we're starting to see emerge.
Which brings us to a crucial point. If you have these complex, multi-step agents interacting with external tools, the potential for unexpected behavior skyrockets. A model's output is non-deterministic by nature. How on earth do you monitor this in a live production environment? This isn't like a traditional application where you can just check if an endpoint is returning a 200 OK status.
This is the problem that an entire category of AI observability platforms is trying to solve. Companies like Arise AI, Weights and Biases, and Human Loop are building the equivalent of Datadog or New Relic, but specifically for AI systems. They recognize that monitoring an LLM application requires a completely new set of metrics. You're not just tracking latency and CPU usage, you're tracking things that are much harder to quantify.
You're talking about things like model drift. What does that mean in practice?
Model drift is when the model's performance degrades because the real-world data it's seeing in production starts to differ from the data it was trained on. For instance, an AI designed to analyze financial news might start performing poorly if new market terminology emerges that wasn't in its training set. These platforms detect these statistical shifts automatically, alerting you that your model's map of the world is no longer accurate.
And they also monitor for things like bias and toxicity, I assume.
Yes, and that's critical. They can track the sentiment of outputs, look for the presence of harmful language, and even analyze how the model is performing for different segments of your user base to uncover hidden biases. They also track hallucinations, when the model confidently states something that is factually incorrect. By embedding all the model's inputs and outputs into a mathematical space, they can cluster them and identify outliers and anomalies that a human reviewer might miss among millions of requests.
It's like having a real-time quality control system. But monitoring is reactive. What about proactively testing these models before they ever see the light of day? We have unit tests and integration tests for traditional software. What's the equivalent for AI?
The testing landscape is evolving rapidly. At the basic level, we have evaluation libraries like OpenAI Evals or Hugging Face Evaluate. These provide standardized benchmarks, basically exam questions, to test a model on a wide range of tasks, from reasoning to code generation to summarization. This allows you to quantitatively measure whether a new version of your model is actually an improvement.
So that's your regression testing.
Precisely, but it goes much deeper. The most sophisticated teams are now heavily engaged in red teaming. This is an adversarial process where a dedicated team or even another AI actively tries to break the model. They look for security vulnerabilities, try to bypass its safety filters, and craft clever prompts to induce biased or harmful responses. It's about finding the edge cases and failure modes before your users do. We're also seeing the rise of synthetic user testing, where you use one LLM to simulate thousands of different user personas and conversations to test your application at scale.
So you have frameworks to build complex agents and observability platforms to monitor them. That still leaves the most important piece, especially for any large enterprise: control. How do you enforce rules and ensure the AI operates within acceptable, predefined boundaries?
This is the domain of guardrails and governance, and it's a non-negotiable part of deploying AI in any regulated or brand-sensitive environment. The approach is twofold: pre-deployment and runtime. Pre-deployment is about building safety into the model itself. This involves carefully filtering the training data to remove undesirable content, training separate safety classifiers that can flag problematic inputs or outputs, and using alignment techniques like reinforcement learning from human feedback to fine-tune the model to be more helpful and harmless.
That's building a foundation of safety. What happens at runtime, in the fraction of a second after the model generates a response but before it's shown to the user?
That's where real-time guardrails come in. You can think of it as a separate, faster, and simpler model or a set of rules that acts as a final checkpoint. It inspects the generated output for specific keywords, checks against a content policy, or verifies that it doesn't contain personally identifiable information before it's sent. It's a crucial final safety net. Many systems also integrate a user feedback loop, like the thumbs up, thumbs down button, which is critical data for flagging issues and further fine-tuning the model over time.
For a large enterprise, this can't just be an ad hoc process. There must be formal frameworks for managing this.
Absolutely. We're seeing widespread adoption of standards like the NIST AI Risk Management Framework in the US and global guidelines from organizations like ISO. These frameworks provide a structured methodology for businesses to identify potential AI risks, from privacy and security to fairness and accountability, and then implement the controls to mitigate them.
The ability to trace a decision.
Exactly. For any application in finance, healthcare, or law, you need an immutable audit trail. You must be able to log every input, every output, and every intermediate step an AI agent took to arrive at a decision. If an AI-powered system denies a loan application, regulators and customers will want to know why. Without comprehensive logging and observability, that becomes impossible to answer. Accountability requires auditability.
Let's pull all these threads together then. It seems the journey from a base model to a production-ready AI application requires building an entire ecosystem around the model. It's not a single component, but a layered system.
That's the perfect way to frame it. The base model, which we discussed in previous episodes on infrastructure, is the powerful but untamed core. The agent framework acts as the strategic brain, giving it the ability to plan and execute complex tasks. The observability platform is the always-on sensory and nervous system, constantly monitoring its health and behavior. And the governance framework acts as the conscience, ensuring its actions align with human values and business rules.
It's this surrounding software stack, the tooling, monitoring, and guardrails that truly makes AI enterprise-ready. It's what provides the reliability, safety, and accountability needed to move beyond experiments and build transformative products.
And now that we have a clear picture of the sophisticated tooling required to build and manage these systems, it sets the stage for our next conversation. With these frameworks and controls in place, what are the breakout applications that are actually being built?
A perfect transition. In our next episode, we will explore the tangible impact of all this technology. We'll dive into specific use cases that are redefining industries. The explosion in code productivity powered by tools like GitHub Copilot and Cursor, the transformation of creative media, and the rapid deployment of enterprise copilots inside platforms like Microsoft 365 and Salesforce. We'll see how the development tools we discussed today are the critical enablers behind these real-world AI success stories. Welcome to another episode of Key Players in the AI Industry. We've spent the last several episodes deep in the trenches of AI infrastructure, charting the rise of the tooling, the monitoring platforms, and the governance frameworks that make this technology enterprise-ready. We've talked about the engine, the chassis, and the safety systems. Today, we put the car on the road.
Exactly. If our last discussion was about the how you build, deploy, and manage AI systems reliably, then this episode is squarely focused on the what and the where. The question on everyone's mind is no longer can it work, but where is it actually working? We're moving past the proof of concept and into production. Today, we're mapping the real-world impact of AI across 4 key domains: the seismic shifts in code productivity, the revolution in creative and media industries, the rise of the enterprise co-pilot in major business verticals, and finally, the cross-domain strategic patterns that are emerging as organizations get serious about scaled deployment.
It's a critical moment in the industry. The rubber is meeting the road, and the results are starting to be measured not in benchmark scores, but in dollars, hours, and market share. Let's start with perhaps the most direct and quantifiable impact we've seen to date: code productivity. Developers were among the first to have these tools integrated directly into their daily workflow, and the effects have been profound. We're seeing mass adoption of tools like GitHub Copilot, but also more specialized AI-native environments like Cursor and Lovable. And with the recent release of models like OpenAI's GPT-5 Codex, the capabilities are taking another leap.
It's a fundamental platform shift. The best analogy I can think of is the move from assembly language to high-level programming languages and compilers. Before compilers, developers had to manage memory and speak the machine's language directly. Compilers abstracted that away, letting them focus on logic and intent. AI coding assistants are the next layer of that abstraction. Developers can now express their intent in natural language, refactor this function to be more efficient, or generate a Python script to parse this API endpoint. And the AI handles the boilerplate, the syntax, and often the complex logic. It's a force multiplier for a developer's own intelligence.
And the use cases have expanded far beyond simple code completion. That was the first wave. The second wave is much more sophisticated. We're seeing AI used for comprehensive code generation, for intelligent refactoring of entire legacy systems, think converting 1 million lines of COBOL into modern Java, and for creating robust test suites automatically. This isn't just about making developers faster, it's about improving the quality and maintainability of the code itself.
That's the key. The impact isn't just anecdotal, it's showing up in the metrics. We're seeing organizations report measurable improvements in what they call developer velocity, the speed at which new features and fixes can be shipped. When a developer can offload the cognitive burden of remembering obscure library syntax or writing repetitive unit tests, they can spend more time on architectural design and problem solving, which is where they create the most value. It's a qualitative shift that produces a quantitative result.
From the logical world of code, let's pivot to the much more subjective and aesthetic world of creative and media. For a long time, this was seen as the final frontier for AI, a domain that would be resistant to automation. That assumption has been completely upended in the last couple of years. Generative AI is now a core component in the pipeline for everything from concept art and voiceovers to marketing content and even video production.
This transformation reminds me of the shift from analog to digital tools in creative fields. When Photoshop first arrived, many photographers and artists feared it would devalue their skills. Instead, it became an incredibly powerful new tool that unlocked new possibilities. It didn't replace the artist, it augmented them. We're seeing the same pattern now. An art director can generate a dozen different visual concepts for a campaign in the time it used to take to sketch one. A podcast producer can create a high-quality voiceover with a tool like 11 Labs or OpenAI TTS without booking a studio and a voice actor.
And the business impact of that is enormous. It dramatically accelerates iteration cycles. In marketing, for example, the ability to rapidly generate and test variations of ad copy, imagery, and even short video clips allows for a level of A/B testing that was previously unimaginable. This leads to more effective campaigns and a higher return on investment. In film and game development, generative AI is reducing production costs for storyboarding, character design, and creating environmental assets.
But this domain also comes with a unique set of challenges that are less pronounced in, say, code generation. The first is brand consistency. How do you ensure that AI-generated images or text adhere to the specific aesthetic, tone, and values of a brand? It requires careful prompt engineering, fine-tuning, and a human in the loop for curation. The second and much larger challenge is intellectual property. What training data was the model built on? Who owns the output? Can you copyright an AI-generated image? These are complex legal and ethical questions that businesses are grappling with in real time.
Those IP and consistency concerns become even more critical as we move into the third area, the integration of AI directly into core enterprise workflows. We're seeing every major enterprise software provider roll out their own version of a copilot. Microsoft has baked it into 365, Salesforce has Einstein, ServiceNow has its own suite of AI tools, and Google is integrating it across its workspace. This is AI leaving the specialized application and entering the mainstream of daily business operations.
This is the embodiment of the idea of ambient computing. The AI is no longer a destination you go to, it's a capability that is present in the tools you already use. It's like when GPS went from being a separate device you stuck on your dashboard to being an integrated feature of your phone's mapping application. You stopped thinking about using the GPS and just started thinking about getting directions. Similarly, an employee will soon stop thinking about using the AI and will just expect to be able to summarize a long email thread, generate a first draft of a report from meeting notes, or analyze a spreadsheet by asking questions in plain English.
Beyond these horizontal productivity tools, we're also seeing an explosion of highly specialized vertical applications. In healthcare, AI models are now assisting radiologists in analyzing medical images, identifying anomalies that the human eye might miss. In finance, they are being used for complex fraud detection patterns and for real-time market analysis. And in the legal profession, AI is revolutionizing document review for discovery, being able to parse millions of documents for relevance in a fraction of the time it would take a team of paralegals.
And what's driving the adoption in these critical, high-stakes fields is a proven, measurable return on investment. A hospital doesn't adopt an AI diagnostic tool because it's trendy. It adopts it because it demonstrably improves patient outcomes or operational efficiency. A law firm doesn't use AI for contract analysis on a whim. It does so because it reduces billable hours spent on tedious work, freeing up lawyers to focus on high-level legal strategy for their clients. The business case is becoming undeniable.
This brings us to our final topic, which is a level up in abstraction. As organizations across these different domains move from isolated experiments to scaled deployments, we're starting to see common strategic patterns emerge. These are the best practices for implementing AI at an enterprise level. The first is what's being called model mixing, or a compound AI systems approach.
This is a really sophisticated and important development. The initial thinking was that companies would simply pick one large, powerful frontier model from a provider like OpenAI or Anthropic and use it for everything, but that's proven to be inefficient and expensive. Instead, smart organizations are building systems that act like a triage nurse. A complex creative query might get routed to a large general-purpose model, but a simpler, more structured query, like summarizing a customer support ticket, might be sent to a smaller, specialized, and much cheaper open-source model that has been fine-tuned on the company's own data. It's about using the right tool for the job to optimize for performance, cost, and latency. It's like having a full workshop instead of just a single sledgehammer.
The second major pattern revolves around deployment strategy. It's the classic debate, cloud versus on-premises. Many companies are using a hybrid approach. They might leverage the public cloud APIs for speed and access to the latest and greatest models for less sensitive applications. But for workloads involving proprietary data, personally identifiable information, or regulated content, they are opting for on-premises deployments or virtual private clouds. This gives them maximum control over security and compliance, even if it means a slightly slower innovation cycle. It's a strategic trade-off between capability and control.
And the final piece of the strategic puzzle is organizational. To manage this complexity, the model mixing, the hybrid deployments, the vendor relationships, we're seeing the rise of internal AI centers of excellence. Instead of having dozens of different departments all running their own separate and often redundant AI experiments, mature organizations are centralizing this function. This central team is responsible for setting strategy, evaluating new models and tools, establishing best practices for security and ethics, and helping to scale successful pilot projects across the entire enterprise. They become the internal consultants and gatekeepers for AI, ensuring that it's being deployed in a way that is coherent, efficient, and aligned with the company's overall goals.
So, to bring it all together, the story of AI in the enterprise today is one of tangible impact and increasing sophistication. We've seen it transform developer productivity, reshape creative industries, and embed itself into the core workflows of major business verticals. And underpinning all of this is the emergence of intelligent, strategic patterns for deployment, mixing models, balancing cloud and on-prem, and centralizing governance. The experimental phase is giving way to the era of scaled, strategic implementation.
It's a powerful transition. But as these AI systems become more deeply woven into the fabric of our economy and our daily work, they cease to be just a technological issue. They become a societal one. The very applications we've discussed today, from generating code that runs our infrastructure to creating media that shapes public opinion and assisting in critical legal and medical decisions, raise profound questions about governance, accountability, and risk.
That's the perfect setup for where we're headed next. Now that we understand how these systems are being used and the value they're creating, we have to confront the rules of the road. What are the legal frameworks and policy decisions being made to manage the power of this technology?
Exactly. The widespread adoption we've detailed today makes the next conversation unavoidable. We'll be looking at the different regulatory approaches taking shape around the world, from the innovation-focused executive orders in the United States to the comprehensive risk-based EU AI Act and the state-controlled governance in China. We will also delve into the critical issues of content provenance and corporate liability, because when AI is everywhere, the policies that govern it become as important as the technology itself. That's all coming up in our next episode.
Welcome to the final episode of this series of key players in the AI industry. In our last discussion, we explored the incredible explosion of AI applications across every sector, from tools that accelerate code development to co-pilots embedded in our daily enterprise software. We saw how organizations are enthusiastically adopting AI to drive productivity and innovation.
That rapid adoption was the what. Today, we're diving into the inevitable and arguably more complex how. As AI becomes deeply integrated into the fabric of our economy and society, a new urgent question arises. What are the rules of the road? We're moving from a period of pure, unbridled innovation into an era that demands structure, safety, and accountability.
Precisely. The wild frontier is giving way to settlements, and settlements need governance. This episode is dedicated to the crucial topics of policy, risk, and compliance. We'll be mapping the emerging global regulatory landscape, starting with the distinct approaches in the United States, Europe, and China.
Then we'll get practical and look at how we can trust what we see and who is responsible when things go wrong, which means talking about content provenance and legal indemnity. Finally, we'll bring it all home to the enterprise level, examining the frameworks and strategies companies are building to manage AI risk internally. It's the essential and often unseen scaffolding that will determine the long-term success and stability of the entire AI ecosystem.
Let's begin with the United States. There's been a significant policy shift with President Trump's Executive Order 1479, titled Removing Barriers to American Leadership in Artificial Intelligence. This seems to signal a clear ideological direction.
It absolutely does. This executive order, issued in January 2025, effectively recalibrated U.S. AI policy by revoking the previous administration's order and setting a new course. The core philosophy is clear: prioritize innovation and American dominance by removing what are seen as regulatory burdens. The administration's goal is to ensure the private sector can innovate rapidly without being smothered by bureaucracy at this early stage.
And this led to the America's AI Action Plan, released in July 2025. What are the main pillars of that strategy?
The plan is built on 3 pillars: accelerating AI innovation, building American AI infrastructure, and leading in international AI diplomacy and security. A key theme running through it is deregulation. fast-tracking permits for data centers, reducing environmental review requirements for AI-related infrastructure, and encouraging federal agencies to repeal any rules that might hinder AI development.
The order also places a strong emphasis on ideologically neutral AI systems. What does that mean in practice?
This is one of the more controversial aspects. The administration has expressed concerns that some AI models are being engineered with what it calls ideological dogmas. As a result, the action plan calls for updating federal procurement guidelines to ensure that government agencies only purchase large language models deemed unbiased and free from such agendas. It even directs the National Institute of Standards and Technology, or NIST, to revise its AI risk management framework to remove references to concepts like misinformation, diversity, equity, and inclusion.
So the U.S. approach can be characterized as aggressively pro-innovation, with a focus on market leadership and minimal top-down regulation, instead favoring sector-specific guidance. How does this contrast with what's happening across the Atlantic in Europe?
It's almost a polar opposite in philosophy. The European Union has implemented the AI Act, which is a comprehensive, centralized, and risk-based legal framework. Instead of a light-touch approach, the EU has created a system that categorizes AI applications based on their potential to health, safety, and fundamental rights.
How does that risk-based classification work?
It's a tiered system. At the top, you have unacceptable risk AI, which is outright banned. Think of government-run social scoring systems or AI that uses manipulative techniques. Then there's the largest and most significant category, high-risk AI systems. These aren't banned, but they are subject to very strict obligations before they can be brought to market. Below that, you have limited risk systems, like chatbots, which face lighter transparency obligations, and finally, minimal risk AI, like spam filters, which is largely unregulated.
What specific requirements do those high-risk systems face? This would include AI used in critical infrastructure, medical devices, hiring, or credit scoring.
The obligations are substantial. Providers of high-risk AI must establish robust risk assessment and mitigation systems. They need to use high-quality representative datasets to minimize bias and accuracy. There are also requirements for detailed technical documentation, activity logging for traceability, and ensuring a high level of cybersecurity and robustness.
The EU Act also mandates transparency for AI-generated content. How is that being enforced?
This is a key part of the limited risk category. The law now requires that AI-generated or manipulated content, such as deepfakes, must be clearly labeled as such. The goal is to ensure users are always aware when they are interacting with an AI system or viewing synthetic media, empowering them to better identify potential misinformation.
And what about the UK's position post-Brexit? Are they aligning with the EU or forging their own path?
The UK is attempting to strike a balance, creating a third model. It's more structured than the US approach, but less prescriptive than the EU's AI Act. The UK has proposed a pro-innovation, principles-led framework. Instead of creating a new central AI regulator, the plan is for existing regulators in fields like finance, healthcare, and human rights to extend their responsibilities to incorporate and govern AI within their specific domains. It's a more decentralized, sector-by-sector approach, but one grounded in shared principles like safety, transparency, and accountability.
So we have three distinct Western models: the US focus on innovation and market forces, the EU's comprehensive rights-based regulation, and the UK's flexible principles-based framework. Now let's turn to the third major global player, China. How does its approach to AI governance differ?
China's approach is fundamentally different because it is state-centric. AI governance is tightly integrated with national policy and social stability objectives. The government maintains strict controls, requiring companies to register their models with the state before they can be released to the public. This ensures that all AI systems align with state ideologies and content policies.
This sounds like a system designed for maximum control. How does it affect the technology itself?
It has a profound effect. Chinese models like Baidu's Ernie and Alibaba's Qin are developed with a primary focus on domestic data and are fine-tuned to operate within government guidelines. Furthermore, China's policies on digital sovereignty, combined with U.S. export controls on advanced semiconductor chips, create a more insular technology ecosystem. This limits the flow of technology both into and out of the country, reinforcing a focus on the domestic market.
With these diverging global policies, a company operating internationally faces a complex compliance web. This brings us to a very practical problem. In a world awash with AI-generated content, how can we verify what's real?
That's the question of provenance. The leading solution gaining traction is a technical standard called C2PA, which stands for the Coalition for Content Provenance and Authenticity. Think of it as a secure digital watermark for media. It allows a creator, whether it's a camera manufacturer, a news organization, or an AI model, to attach metadata that verifies the origin and history of a piece of content.
So if an image is generated by an AI, the C2PA metadata would specify that?
Exactly. Major AI labs are already implementing this. For example, images generated by DALL-E 3 via OpenAI's tools now include C2PA metadata. This metadata is cryptographically signed and tamper-evident, creating a chain of trust. Anyone can use a verification tool to inspect the content's credentials and see if it was AI-generated, who created it, and if it has been subsequently edited. It's not a silver bullet, the metadata can be stripped away, but it's a critical step toward creating a more transparent digital ecosystem.
Provenance tells us where content came from, but what happens when that content causes harm? If a company uses an AI system that generates faulty advice or infringing content, who is liable? This leads us to the thorny issue of indemnity.
This is a major point of negotiation in every enterprise AI contract today. AI vendors have historically tried to disclaim all liability for the outputs of their models, putting the entire risk on the customer. However, as enterprises become more reliant on these tools, they are demanding stronger contractual protections. They want the AI provider to indemnify them, that is, to cover the costs if the customer gets sued for issues like copyright infringement arising from the AI's output.
So the market is starting to shift from use at your own risk to a shared responsibility model.
Precisely. We're seeing AI providers beginning to offer certain levels of indemnification as a competitive differentiator, but the details are incredibly important. These clauses need to be carefully reviewed because they often contain exceptions. For example, a vendor might indemnify against copyright claims, but not for other risks like inaccurate outputs, data breaches, or algorithmic bias. The scope of the indemnity and the cap on the limitation of liability are now critical battlegrounds in enterprise software agreements.
All these external factors, disparate global regulations, new provenance standards, complex liability negotiations, must be managed internally. This brings us to our final topic: enterprise AI risk management. How are companies structuring themselves to handle this new reality?
They are building formal AI governance frameworks. The era of letting individual teams experiment in silos is over. Mature organizations are establishing internal review boards or AI centers of excellence to create a centralized approach. This involves conducting comprehensive impact assessments before deploying any new AI system, performing regular security audits, and ensuring compliance with data privacy regulations like GDPR and CCPA.
Are there standards that guide this process?
Yes, two frameworks have become the gold standard. The first is the NIST AI Risk Management Framework, or AIRMF. Released in 2023, it's a voluntary guide that helps organizations structure their approach to AI risk through 4 functions: govern, map, measure, and manage. It provides a common language and systematic process for identifying, assessing, and mitigating AI risks throughout the system's lifecycle.
And the second framework?
That would be the new international standard, ISO/IEC 42001. This is a formal management system standard, much like its famous cousin, ISO 27001 for information security. It provides requirements for establishing, implementing, and continually improving an artificial intelligence management system, or AIMS. Achieving ISO 4201 certification allows an organization to demonstrate to regulators, customers, and partners that it has a robust, process-driven approach to AI governance.
It sounds like the key takeaway from our entire discussion today, and perhaps for this entire series, is that AI is growing up. The industry is moving from a phase of pure technological discovery to one of scaled, responsible deployment. The focus is no longer just on what AI can do, but on what it should do, and how to build the guardrails to ensure it operates safely, fairly, and reliably.
Exactly. The key players are no longer just the frontier labs building the most powerful models. They are also the policymakers shaping the rules, the standards bodies creating trust, and the enterprises meticulously building internal governance frameworks. Sustainable success in the AI industry is no longer just about having the best algorithm. It's about building the most trustworthy and compliant ecosystem around that algorithm. This fusion of innovation and governance is the defining feature of the next chapter in AI. As our series concludes, it's clear the future of AI will not be written in code alone, but also in policy, standards, and the careful practice of risk management.